Gravitational potential energy is going to be the first type of potential energy that we work with. And we're going to put a sub G, capital or lowercase is fine, on capital U to make it clear that we're talking about gravitational potential energy. And at least on Earth, gravitational potential energy is the mass of the object, that is not the Earth, times g, where that's 9.8 meters per second squared, times the distance or that you are up from your 0 point. Note that if we want to consider gravitational potential energy, our system now actually includes the Earth, or at least enough of the Earth to have gravitational potential energy. So we consider this interaction, the gravitational interaction between our object and the Earth, to now be a form of energy itself. Now this is going to be in place of calculating the work done by gravity. I think it can be very confusing to talk about the work done by gravity and get the signs correct, so instead you can just talk about potential energy. Now note that this is only depending on height, also the mass of our object, but it doesn't depend on how fast the object is going. The other thing to note is that to really define y, we must have a zero value defined for y. Now, we're going to talk a little bit about how much it matters for this actually to be defined. This is part of where it matters that you define your coordinate system. Where is zero and what direction is positive? And again, this scenario where we call this y here, we are assuming that the vertical direction, the one gravity acts in, is y, and that up, away from the center of the Earth, is the positive direction. Something that is a little confusing about gravitational potential energy is that you can actually define zero to be in different places. And the reason that that is okay is because really when we go to make calculations, we only care about changes in potential energy. So for instance, if you are perhaps in your dorm room watching this video right now, maybe you're on the second floor. So you might think that the floor of your room has zero potential energy, but obviously that's not the same height as, for instance, the ground outside. You could drop a ball out your window and it would be able to go much lower than it would if you were simply in your room. So this is again where it's important to define clearly your coordinate system, because in this picture, Amber says that this rock is 1 meter above the ground. Carlos says that the ground is 1 meter below the rock. They've chosen different points to be zero. But notice that both of them have defined the positive direction to be up. So that works since they both agree that gravity points down. The delta y in this case is the same. We would say that the delta y is equal to -1 meter in both cases because that's y final minus y initial. So please define your coordinate system, and as long as you are careful about your positive direction and how things are changing and you get your signs right, your calculations will still work out even if you put zero in a different place. As mentioned before, gravitational potential energy only depends on the height of our object. So if we imagine a ball that is at different heights above the ground and has different speeds, the speed does not impact its gravitational potential energy at all. The direction of the velocity does not impact its gravitational potential energy at all. We would say that B and D have the same gravitational potential energy, again, the system of the ball with the Earth, because they're at the same height. Ball C is at the highest point and has a velocity of zero. It has the most potential energy because it's the highest. So again, don't try to bring in other variables, and that's where it's important to understand how to distinguish the different types of energy and use them independently in your equations since they're different. Kinetic energy relates to the speed, but potential energy does not. Where this also comes in is that when we're thinking about an object that is traveling in both x and y, to think about how its gravitational potential energy has changed, we only need to think about a change in height. It's true that this block has also moved in the x direction, but all we care about is the change in height. Note that in this case it does say it's a frictionless surface, and that's only important for knowing that we don't have to worry about thermal energy. The friction or the lack of friction doesn't actually change our potential energy, but it does influence other types of energy. So to talk about the initial potential energy of this block, we just define our zero position, this dashed line, and so we would use the height above to be multiplied by m and g to get our initial potential energy, and to get our final gravitational potential energy, we would multiply y final, which in this case is equal to 0. So the fact that this has traveled in a direction that I would likely call x, that doesn't actually influence our gravitational potential energy at all. So this is one simple way to take a two-dimensional problem and at least think about gravitational potential energy in a more straightforward way.